Welcome to the Physiological Society. It's lovely to see so many people who've responded to the advertising campaign we've been running on all BBC channels for the last 2 weeks. My name is Michael Hutchinson. I am here to introduce tonight's talk, which is The Science of Cycling, How to be an Elite Cyclist. And speaking as someone who was an elite cyclist for 10 years and never quite felt I was getting it right, I am genuinely very curious to see what we're going to hear tonight. If there's anyone who can tell us what it takes to be an elite cyclist, how you make an elite cyclist, it is Professor Louis Passfield from the University of Kent. Louis is an enormously experienced sports scientist and exercise physiologist. And as well as his academic interests, he has been lead physiologist with the British Olympic cycling team in 1992 Olympics, 1996 Olympics, and for the all-conquering breakthrough 2008 Olympics in Beijing. So if it wasn't for Louis, I think I would be confident in saying none of us would ever have heard of Bradley Wiggins. Is that fair, Louis?
Not at all, but I'm quite happy that you said that. Thank you.
As well as his academic and his practical team work, Louis was also a very distinguished racing cyclist himself in the relatively recent past, I think would be fair to say, and was in 2006 at the Melbourne Commonwealth Games for 4.5 memorable but catastrophically unsuccessful minutes my pursuit coach. The catastrophically unsuccessful bit of it was all my fault, and the memorable bit of it was all Louis' fault. So I'll introduce you to Louis, and I can't wait to hear what he has to say.
Thank you very much, Michael. It's a real pleasure to be here. So thank you all very much for coming this evening, and also to the Physiological Society for inviting me too. I'm one of those fortunate people that gets to play for his work, and so being a sports scientist means that it's always easy for me to get up in the morning and carry on with wherever I've left my work from the night before. And so I have a real passion in sharing something of what I do. One of the things that I'm always very proud of is the fact that I've been able to combine both academic and practical work. So Michael's talked a lot about the applied work that I've done with British cycling, but I've also worked within academia on the research side as well. What I'm going to do this evening is just give you a few snippets from a sort of personal story or journey, if you like, on different aspects, as much to prompt questions from you. So the brief that I've been given is to talk for about 30 minutes or so and leave plenty of time for questions. So I'm hoping that I'll be able to do that, if not by at least the fact that I won't answer any useful questions in the process of my talk. So the useful questions will have to come from you at the end. So that's a warning for you, if you like. I often just give a brief introduction to myself to people because I've been in sports science now for way longer than I can remember, so I put it on the slide. And my motivation for going into sports science was that I wanted to be the first Briton to win the Tour de France. So my plan was that I'd study sports science and then this would have happened instead. But unfortunately, by studying sports science, I learned 2 rather more painful lessons than I expected. The first one is that sports science doesn't have all the answers that I was looking for. So if you've paid this evening and you're expecting some scientific basis to any answers about how to be an elite cyclist, then you might want to ask for a refund now and save any more time. The other lesson I learned was that I was born at the wrong time in the year and lacked the talent, consequently, to actually achieve my dream. But what I did find was that shortly after graduating in sports science, I was in an Olympic training camp, but as a scientist rather than as an athlete. And this was a much better way of enjoying the benefits of high performance and the privileges of going to Olympic Games, Commonwealth Games, World Championships, and so on. And so I've kind of been stuck in this rut for the last 25 odd years. So that's really kind of just a little bit about me and my background. But the key thing there is my passion has always been about trying to enhance performance, and particularly my own performance. And as I get a little bit older, I become increasingly interested in trying to extend the benefit of my experience and the privileged opportunities that I've had to a much wider audience. So tonight, just very briefly, what I'll do is touch on 3 very broad areas to try and tell a story. Firstly, just to look at a little bit of work I've done around understanding the demands of elite cycling. Then a little bit looking at elite riders and their performances. And what I've tried to do is stray from some of the most obvious stories and things that you would hear from standard physiology textbooks or standard physiologists, if you like, and just pick out some things that might be a little more quirky or interesting. And then my real passion is training and the study of training. And this is an area which is surprisingly unscientific. So there's definitely no answers here, but I'll kind of try and give you a sense of what I'm looking at the moment and where we may be headed in the future. As I said, with a view to you asking whatever questions that occur to you as we go through. So to start off with, I just thought my very first piece of research was based around using power meters, which is a device that you can attach to the bicycle, and many of you in here may already have them, where you can measure exactly how hard someone is working on their own bicycle as they're riding. So it makes cycling a wonderful sport for scientists because we can analyze things, we can gather huge amounts of data and analyze that in great detail to try and better understand what a performance takes. But it was back in 1992 that I first got my hands on a device like this. And so it was only from about that time onwards that we were able to understand really what the demands of elite cycling were. Prior to the invention of these devices, and they were actually developed by a really smart East German back in the 80s, but they didn't sort of make their way into Europe until much later on. But prior to that, we had to make any estimations about what it took to be an elite athlete from our observations of elite athletes in the lab. And so there was always a question about whether we were measuring the right things in the lab and whether what we measured in the lab actually corresponded with what happened when someone actually started racing. And we really had no idea about that. And then it was also coupled with the fact that at that time cycling was a rather amateur sport in the UK, and we had very few British role models that we could look at to try and understand what elite performance was all about. So this was a huge step forward for us. And then the lottery funding, when it came online in '96, changed the shape of British cycling at a time when actually I stepped back. So what happened was then British cycling evolved rapidly to the kind of force that we see today in international competition. And then I came back in around 2006 to see this completely different sport, which was then hugely exciting to work in. But the first piece of work that I was involved in doing was trying to understand the demands of track cycling, because up until that point, no one had been able to measure how hard it was to race on the track. And an obvious starting point was to look at the hour record. And because one of the most famous athletes in the world of all time, Eddie Merckx, had set one of the hour records, this was something that was really quite prestigious within cycling. And then a few years later, Francesco Moser in 1984 broke Merckx's world record. And this sort of resurrected interest in the hour record, not least because he did it by using some substantial technological innovations. And so the question was Merckx a better athlete than Moser, or did Moser beat Merckx's world record because of the technological innovations? And then, because that had stimulated this interest, there was then a sudden rush of new world records, fueled particularly by the rivalry of Graham O'Brien, the Scot, and Chris Boardman. And we saw this evolution of world records starting from 1876 here, with the first established world record of around about 26 kilometers an hour, 25 and a half. And you can see the steady increase in world record performances up until this time here, where Moser then triggered this interest, and then this rapid rise up until the record that Boardman set in 1996. This paper was published in '98, which is why it stops then, but also the UCI changed the rules at that time too. So we were really focused on looking at this period here and trying to understand what had happened to performances. Was it better and fitter cyclists that drove these increases, or was it changes in the riding position? So to give you a prompt in your memory of how this might have looked, this would have been the sort of traditional racing position that Merckx would have used when he set his world record. And then Moser came along and introduced an aerodynamic helmet and an aerodynamic bicycle. So a quite radically different setup, and particularly solid wheels as well. O'Brien in '93 set a world record with a kind of saw your arms off cycling position, where he bent over like this and rode in this sort of position, which was incredibly aerodynamic. And then that position was outlawed, but further refined to a Superman position, which looks something along the lines of what we see in our elite cyclists today. And so we were just curious to say, well, okay, was it the changes in position that drove this, or was it actually the rider's own level of performance? I'm going to jump forward a few years to just bring in another aspect to this, but I'll come back to the answer in a second. In essence, what we're able to do now is to take a real bicycle and then put it into a computer. So we build a cycling model. So this particular model that we've got here, and this is one I worked on with a colleague at the University of Brighton, Patrick Kangley, who has essentially taken every aspect of this bicycle and created it within a computer within a mathematical model. It means that we can now change any aspect of that rider and the bike, send it round a track, and estimate how fast that bike will go or how much power is required to go at any different speed. And what we did was, with the hour record study, was a precursor to this kind of analysis, where we made estimations about how hard it would be with a different equipment to ride at those different speeds. I'll skip that slide. There we go. So this is the last few world records that we see on that previous graph of the evolution of the hour record, and you can see the change in the distance that was achieved for all the riders from 51.15 kilometers up to 56.375 kilometers. And then here you can see how hard we calculated the riders had to work in order to achieve these speeds. And essentially, what happens is a nice pattern falls out of this. So the colours here are not simply to give contrast between the successive world records, but actually the black lines indicate where the new world record was established by a higher performance than the preceding one. In other words, the rider had to be fitter. The red lines show that the performance was achieved by a lower performance, a lower power output. In other words, the rider was actually taking advantage of a technological innovation that enabled him to cut through the air more easily and actually wasn't as fit in order to do that performance. So what we can see here quite nicely is how our record is first broken by more of an innovation, so the power output is lower here to go for this greatest distance or for higher speed. Then the power output increases again, it decreases, it increases, it decreases, it increases, decreases. So actually we see a combination as you scan down that line there of an evolution in terms of technological design and people going faster because of the changes in equipment. And then also an increase in performance because these riders are starting to be able to produce more power. And our crude estimations of the hour record today as it stands would have us in broadly this same sort of category as we are now. So it's likely that the current hour record is still produced by a power output in this kind of range of around 430, 440, maybe 450 watts. That seems to be very close to the kind of human limits that the best and most elite cyclists can achieve. And it's hard to appreciate exactly how much of a superlative performance that is. But I just thought I'd put a little note here is that this performance here is around about 2.5 times as much power as a normal person could achieve with a modest amount of training. So the guys that are setting these world records are 2.5 times or 250% fitter than we are. And that theme of developing power and changing our performance is something that I'll come back to a couple of times during the talk, but that's just why I wanted to bring that out. If I pause for a second, has anyone got a question on something I need to clarify? Or
sorry.
Yes, please do.
About the power voltage and the technological differences.
Yes.
How factors like altitude, so and I think Moses set his Mexico City, which they said part of that was going to be altitude.
Absolutely, that's a really good question. Yeah, so one of the things that Moser did as well, and Merckx before him, was to use altitude in order to try and benefit enhance their performance, because at altitude the air pressure is lower, and in cycling about 90% of the work we're doing is overcoming air resistance. So if the air pressure is lower, it's easier to cut through that air, and therefore we can go faster. The trade-off is that from a physical perspective, we actually compromise our own body's performance too. So there's actually a fairly delicate balancing act in terms of what the benefits are of going to altitude versus how much your performance is compromised because you can't work as hard. So in short events, for example, sprints, you would definitely expect to see better performances. And for example, Chris Hoy went for the kilo world record at high altitude because that would represent an ideal environment there where you're not so worried about being able to get oxygen from the air and your performance in theory is less compromised. For something like the hour record, there's a debate about whether that's going to be really effective or not. So it is a variable, and actually our original study, we made some estimations about that. But one of the things that we found is that riders are hugely variable in their ability to cope with altitude. So some riders can go to altitude and find they don't experience huge decrements. Other riders feel it quite markedly. And interestingly, in the lab at Kent recently, we had some guys from the GCN network who run the little video blog. And the two of them went into simulated altitude in the lab. And one of them commented that his best international performance, this is Matt Stevens, was when the World Championships were in Colombia at altitude. Whereas the other presenter, Simon Richardson, said he'd never perform well at altitude, which is unfortunate because he's a mountain bike rider as well. And in the lab that day, that's exactly how it worked out too. Matt's performances did change a little bit, but not hugely when we put him into the altitude chamber and simulated altitude. But he wasn't too badly affected. Simon almost sort of appeared to run into a wall and grind to a halt as a consequence. So there appear to be those kind of differences too. So it's hard to say, sort of there's a specific altitude that everyone should aim for. Rather, if you could, you might have an adjustable velodrome that you would move to different heights for different riders, which is obviously not so practical. But it's a good question. Thank you.
Yes. Question. So I forget because there's so many record attempts who the second to last one for Wiggins was, but they produced 460 watts per hour.
Yes.
So if you had that person producing 460 watts on Wiggins' bike,
yes,
then
okay. And
by default, would that mean they would go much faster and go further?
Just for clarity, although we think these numbers are probably fairly relevant today, these actually still date back to the 90s. So this isn't the most up-to-date ones, which is perhaps partly why you don't recognise the numbers exactly. So this number here isn't Bradley Wiggins, but that probably is this range here is probably a reasonable estimation of his power output today as well. This record here is actually Tony Rominger back in '94, I think it was, beating Miguel Indurain. Yes, this is Indurain's world record here. So yeah, this was an astonishing ride, absolutely. Yeah. But thank you. Okay, so what I'll do now is move on a little bit. So what I wanted to do was just sort of give some idea of what elite performances look like and how demanding they might be. And then think about actually analysing riders' performance. And I'm going to take a completely different tack from what you might expect from a physiological perspective, but just to throw up a couple of quirky or interesting questions. And the data I'm using here is a study that I did with a colleague of mine from the University of Kent, James Hopker, which basically means he did all the work and I'm taking the credit and borrowing his slides. But we did talk about this data and the study quite a lot. And what we actually did was think there's an awful lot of information now available, courtesy of the internet, on riders' performances historically. And we wondered whether we could actually, if you like, crawl over the internet, gather a lot of that information together, and ask some fundamental questions about riders' performances and the evolution of riders' performances. So what we were able to do was to focus on 25 major races, things like the Tour de France, some of the the early season classic races, and look at the race performances of the riders in these 25 races that we'd earmarked to catalogue them all. So we ended up cataloguing results for around 410,000 different rides, if you like, or race results. And that comprised of nearly 6,000 riders. So we've got results for 25 races for 6,000 riders, which is about 410,000 results. And we took the period dating from 1980 to 2014 because that's where we found we could get what we thought was a reasonably comprehensive and reasonably reliable data set, courtesy of some helpful websites. So that was where we kind of started from. And then we asked a couple of what we thought were interesting questions. The first thing we thought of was to say, well, what age do most riders seem to perform at their best? Now, obviously, as you appreciate, particularly with road racing, actually measuring performance is a little difficult here. You could just pick the winners, but sometimes riders will do a great ride for a team member, or there are all sorts of other things that might happen, bad luck and so on. So rather than just pick winners, we thought we'd look at top 10 placings and then relate it to the age of the riders. So what you see here is the number of top 10 places from our big data set, and then the age of the riders here. And effectively what this curve is telling us then is what's the optimal age for a rider to get into the top 10 of any given race and essentially in this instance, it's those 25 races that we've catalogued. And you can see that quite clearly this curve shows that we get a little spike at 18 years old, and that's really an artifact of the fact that junior riders move to the senior ranks at 18. So the older riders tend to do better at junior level, so the 18-year-olds tend to outperform the 16 and 70-year-olds. So that's why you get this little spike here. And then their performances drop quite markedly. So it's very unusual to see 19 and 20-year-olds getting into the top 10. But then as they start to get older, you can see the number of top 10 placings starts to increase markedly, and it peaks at around 27 years old. So it appears to be that on the basis of the performances that we've been able to analyse from 1980 to 2014, the optimal age for a rider to get into the top 10 is 27, 28 years old. And then as you can see after that, their performances or the number of top 10 places starts to drop away. And then it's unusual to have anyone going much beyond 35 or 36. But we did have a few cyclists ride out to 45 years old. So again, one of those interesting things is like, what's the optimal age for a rider? And it appears to be the answer is around 27. We did the same thing exclusively for stage races as well. So we looked at the Tour de France, Giro d'Italia and Vuelta in case that gave us a different result. Because there's some discussion that for those races, you're perhaps a little bit older. But actually we found the curves were almost identical, that the peak happened in almost exactly the same place if we were looking just at stage races alone. So anyone in the room that's around 27 years old, then you're about your prime for a top 10 place in a top European race. Another thing that we were also interested in is, well, what proportion of riders actually can get into the top 10? And so this was an interesting one, because what we were asking here is, do the majority of professional riders actually get a top 10 placing at some point in their career? Or is getting a top 10 placing actually an unusual occurrence? And again, this was something that previously, as far as we were aware, hadn't been looked at. And actually, the answer was so dramatic that we've had to doctor the slide or the graph here because we can't illustrate it very clearly or easily. So what we're looking at here is, this is the percentage of riders that achieve top 10 places. And then along here is the number of top 10 places that a rider may achieve over their whole career. So the 0 here indicates the number of riders that have not achieved a top 10 placing at all. And actually this bar goes straight off the scale right up to the top, because the answer is it's 78% of all the riders that we looked at did not achieve a top 10 place in their career at all. So when we're looking at the professional peloton and we're watching all of those riders going through the Tour de France or whatever it is, 78% of those riders never achieve a top 10 performance. And then you will see that what happens is that then these performances actually fall off a cliff pretty sharply. So 8% of the riders get one top 10 performance. And bear in mind, we've picked out some of the most prestigious races here. So there may be smaller races that some of those riders do achieve performances in, but we were looking at the really high profile races. So only 8% of riders get one top 10 win in their whole career, and only just over 3% get 2 wins. And then you can see that we've got this decreasing tail of riders that gain 4, 5, 6, 7, 8, 10 places. So what we learned from this is that on average, and this is probably a slightly misleading statistic, riders achieve one top 10 place in their whole career in a very prestigious race. But actually, probably more relevant here is the median figure, because this is skewed by the huge number of zeros and the very large number here. So most riders don't achieve a top 10 place ever in their career in a prestigious race. But what we do see then is this small tail of riders that are incredibly successful. So actually it appears that even in an elite group of riders, there is another super elite group, which is a very small clique of riders that achieve multiple top 10 places. There are only a very small echelon of riders that are capable of placing in the top 10 on a regular basis. And these are presumably those highest earners in the peloton. The vast majority of riders are there to make up the race and will probably never see the front at the finish. Then the last thing, and the reason that I mentioned my birth date, and I actually went to the trouble of looking at Michael's before I came here as well, and he bucks the trend, that or he's not an elite rider, is that there's a well-established pattern in in elite sport, not just cycling, but in other sports, and particularly team sports, football, and so on, where the time of year that you're born impacts on your likelihood of being successful in sport. Now, it's tempting to be cheesy and call it astrology, but in actual fact, it does appear that the Aquarians and the Capricorns and Aries athletes outperform other athletes when you look at what happens in elite sport. This hadn't really been looked at in cycling, so we went back through all of those results again, and we asked the question of those people that are placing in the top 10, when in the year were they born? And what you can see is a clear pattern emerging from this data, where you can see that the overall trend is quite clearly that there are more people winning races who were born at the beginning of the year than there are at the end of the year. And this line here, the stats behind this are a little bit complicated, but this line here indicates this is what you would expect if the time of year made no difference at all. Everyone would be clustered around this black line. What we actually see is January, February, March are all quite clearly above that line, and then as the year progresses, the trend comes down to this average and then drops below it for people in October. Michael's birthday is in November, I believe, and December. I'm a December, so that's my main excuse for why I didn't win the Tour de France, coming back to right at the start, you see, is I was born at the wrong time of year. Perhaps if I could have just held on for a little bit longer and been born in January instead, then everything would have been fine in terms of my aspirations. But it's an interesting observation, this one, and it raises some intriguing questions about the nature and nurture of elite cyclists. You look like you have a question.
Is that specifically for cycling, would you say, or was that trend also seen across all sports?
Yes, so this particular analysis that I'm showing you here is just for cycling, but the same pattern has been seen in many sports. So, I've discovered that Google's quite good at giving you the birth date of famous athletes. So you can say, what's the birth date of so-and-so, and Google will tend to throw that person straight back at you with a birth date. So it's quite interesting to just do a kind of little dipstick audit in different sports of famous people and see when their birth dates are. But you do tend to find a pattern where this emerges, where people born at the beginning of the year pops out. Yes, sir?
Is that different per region? Because say in the UK you might have academic years starting September to whenever it finishes in summer. And then in other places you start in January to December.
So, and this is one of the concerns within academia and schools in particular, is that you see academic performance following a similar pattern but based around school years instead. So that the older pupils tend to do better there in an academic year. So it's not based around the same. It doesn't flex around the same date. And I can't remember which sport it is now, but the time that they move between junior senior is bounded in a different way, and the birth date pattern follows in exactly the same way. I should have done a little bit more reading before I came in this evening to anticipate that question, but absolutely. But I think it's also really interesting in that it really challenges us on what the kind of the nub of nature and nurture is in all of this, that we see this clear pattern and some rationale for why that should be emerging. But depending upon what time of year you're born, it can have an effect on this. And then it's curious to think, well, what would we do if we were trying to scoop up some wasted talent here? Are there people that have the capacity to outperform, but because of the time of year they're born, they just lose out on some of those key developmental opportunities because they're slightly less mature, slightly underperforming, and escape the coach's attention, for example, and don't get moved on or given the same competitive opportunities?
Is there any research into why there's such a big difference between December and January when the actual time could be such a short period?
I think that the main reason is simply that, for example, in cycling, if you're born on the 1st of January, you'll be competing with people who are then, you're in the youngest of that cohort. The cut-off date is the 31st, so anyone born on the 31st of December will be the youngest person in that racing year. And then when you move to the next year, you've got a whole group of people, some of whom are almost a year older than you. So that's the difficulty. So at 16, 17 years, those extra 11 months that some people have seems to make a difference to their ability to perform, gets them noticed, and therefore they appear to have an advantage from that, which then persists throughout their whole athletic career. It's a curious one. Yes.
Slide. Is there any correlation between the number of wins somebody can get and their actual function within the team? For example, if I'm a domestique in a pro team, it's highly likely I'm never going to get a win, but my job is to be a pro cyclist. But Mark Cavendish or Chris, Chris Froome might get that.
Experience would tell us that would be the case. And we had hoped to be able to look at something like that, but actually the challenges of pulling out this information from that extent of data meant that we couldn't break it down in the way that you've suggested. One of the other things that we really wanted to look at, and our main motivation, was to try and look at young riders and how successful they were as young riders, and whether they then went on to be the most successful riders. But again, even that was very, very difficult to pull out. We couldn't get a confident answer from our analysis in that. But can you identify a world champion at 16 and see that pattern continue throughout the whole career? And actually, we found all we could do is just profile individual riders and say, this is the period of time they were racing for, this is when they started winning, and then just look at individual riders. We couldn't say there's a clear pattern here. The analysis was too complex, at least for us in the first instance on that one. So breaking it down into different roles within the team, we just haven't been able to look at that. But logically, you would expect that to be the case.
Sorry, weights
Yes.
places per rider for the GC races. I'm guessing you mean the overall GC after 21 days rather.
Exactly. Yes. But we did look at individual stage results too. So we counted every single stage as a potential race. Okay. Well, I'm glad I've prompted some questions already, and I hope that gives me an excuse to run a little longer in terms of what I promised you in terms of keeping to 30 minutes. But what I thought I'd do now is just look then at, well, we've seen a little bit about what elite performance takes, and we've seen some factors that can influence that performance or dictate the level of success or annotate the level of success of individual riders. And I thought it'd be interesting to focus towards the end of my presentation on the training side. And again, returning to this aspect of nature and nurture. What I've done here is shown you some data from a classic study and a much heavily publicized series of studies that was performed by Professor Bouchard and published back in 2000, which looks at the genetics of training. And it essentially asks, is there a genetic link between how well people respond to training or not? And this was a huge study conducted in the United States across the 90s. And they conducted this study in several different universities because they recruited almost 500 people to their study. And then they trained them for 20 weeks. And they looked at their change in fitness as a consequence of that training. But they were very clever in that what they also did was when they recruited their nearly 500 people, they recruited them in family groups. So you have 500 people, but with little family clusters, so people from the same household sharing some of the same genetic material, so that they could then look to see whether there was a kind of closer agreement between those people from similar family groups compared with people from different family groups. And in this way, start to disentangle whether genetics plays an important part in training. And in terms of the genetic role of training, the answer is very, very mixed. And what I do is just kind of pull a few little bits out of this, which won't give you any specific guidance, but just hopefully serve to confuse you further and make me sound a little clever. What this graph shows is this is the number of people in the study and how much they actually improved as a consequence of 20 weeks of training. And one of the first things we note that actually there is a very small group of people, around about 10, who didn't improve at all as a consequence of training. So they did 20 weeks of training, and at the end of that study period, they hadn't improved at all. Now, initially scientists were a little skeptical, and they thought maybe that, this is just a measurement error or whatever, but these kinds of observations are fairly regularly repeated. So we do seem to find that there are people that don't respond very well to particular types of training. So it's not entirely surprising. Then what we see is a spread of increases in fitness. And crudely, this is around about a 10% increase in fitness, somewhere in this region here. So the vast majority of people over 20 weeks are improving their performance by around about 10 to 15%. Now, when I showed you that first slide, we looked at the power output of the world record performances for 1 hour. And I made the comment that those people were performing at around about 250% above a normal person's level of performance. So here we've got a study where people have trained for 20 weeks and they've increased by around 10 to 15%. So you can see if you're going to make up a gap of 250%, you've got a fair amount of work to go. And it's interesting that actually within sports science, that kind of rate of progression isn't something that is very heavily focused on. So although this study is very well known, the implications of, well, how much can people improve by? And what would you expect if you were starting from here? How long is it going to take you to get there? Is a question that most athletes are very interested in. Whenever I've been testing people, they've always said, okay, that's my result today, but where can I be in a week's time, in a month's time, in a year's time? And we kind of tend to shrug and say, yeah, I'm not really sure. But this data gives us a kind of a first insight purely from looking at across a population at what might be possible. But notice that, that in this particular graph here, the very top level seems to be to gain 1,000 units of increase in fitness here. And there appear to be around about 5 people that make that kind of progress. As we've got a cohort of around 500 participants, that's 1% of that group of people that have increased by around about this 1,000 unit. And I'm going to come back to that particular amount of improvement in a moment, which is why I'm pulling it out now. But so you can see that broadly there's this a kind of normal distribution of improvement in fitness that's based around 10 to 15% increase in fitness as a consequence of 20 weeks of training. You look like you had a question.
Yeah, I was going to say, did they measure, or did they compare kind of those people that improved the most? Could they be the most unfit people that they had in the study?
They did look at that factor. So they said, is the amount you increase related to where you started from? So someone with a huge increase, is it just because they weren't very fit to start with? That would be an obvious one. And they found that no, that wasn't the case. So they were able to rule that out as the starting level of fitness as being a major kind of a confounding factor, if you like. That wasn't the case at all. What they did find, because as I said, genetics is part of this, it was part of the basis of the story, is there is a genetic link here, but it's not very strong. So it accounts for around 20 to 30% of the improvement that you see. So there was a definite kind of clustering around family groups. So you could identify some families where they did respond much more markedly to training than other families. But by and large, the genetics didn't explain the whole picture, which was what they had anticipated that genetics would play a significant role. And so they were surprised at how little or how small a role it played. And since that time, we've seen this pursuit of what are the genes that make up elite performance. And to date, we're still struggling to find anything that we can identify with any conviction. That hasn't stopped some companies from sort of selling you genetic tests to say, you know, send us a sample of your saliva or any cellular material, and we'll make a prediction about what sports you're good at. But from what we can tell so far, actually, it's very, very difficult to make any meaningful prediction at all from simply a genetic profile. And that includes training as well. I hope I haven't contradicted what Yanis said when he was here 2 weeks ago. So I wanted to just look in a little bit more detail then at, you know, what does it take to increase performance? How do we get to that 250% or 2.5 times the normal performance? And I asked one of my colleagues, Chris Fullerton, who works with me, just to have a quick look at some studies that have looked at training in recent times, and then what kind of performance effect they've reported. And so here we've picked out 3 studies. We've got one from Alfred Nimrichter where he studied riders for 4 weeks, and they improved their performance in 4 weeks by 2.6 to 4%. So that gives us a little bit of feel for what we can expect. Bengt Ronestad over in Norway, he did a study where they trained for 12 weeks, and they saw a 4.6 to 6% increase in performance. So a longer study, a little bit more improvement in performance, but still very consistent with the kind of improvements that we've seen on the previous slide. And then again, the same with this Silter study here. And these are just 3 studies that we've picked out as being reasonably well-controlled recent studies that show a typical performance effect. And actually, I had one of my previous research students do a similar sort of exercise, and she condensed a whole load of studies looking specifically at cycling-related training. And she found around about 15 or 20 studies that we catalogued. And overall, with all of these studies, they were conducted for 9 weeks, so 9 weeks of training. And on average, over 9 weeks of training, they found an effect of about 11% increase in performance over that time. So it kind of gives you a feel for what sort of increase in improvement can be seen. But under these circumstances, it's perhaps worth also thinking about, well, what's the minimum and the maximum that you might be seeing as well? And although I haven't recorded the actual minimum maximum here, a surrogate for that is say to what's the variability or the spread in that data? Are they widely spread, or are they very narrowly and tightly bunched? And we use the standard deviation to measure that. And so in terms of the length of the studies, they varied by around plus or minus 5 weeks. So some studies were up around 14, 15 weeks, or maybe a little bit more. Some were down at only 4 or 5 weeks in this tabulated data here. But the variability in the change in performance was huge, 9%. So some studies were seeing effects of over 20%, others were seeing maybe only 1 or 2% change across that whole period. So what we're seeing here is a pattern where training studies are actually delivering highly variable responses in terms of the benefit to their fitness, which is kind of complicating the story a little bit already. So we're seeing there's this massive discrepancy between where normal people are and what we know elite performance is. But we're also seeing that actually the training studies that are conducted, some people seem to be quite successful, others less so. We know that there's a small but not huge genetic component to that. But these changes that we're seeing appear to be highly variable. This is the slide that I showed you before, and I said that I wanted to pick out this group of those that increased by more than 1,000 units here on that last slide. And the reason I wanted to do that was because there was a very early study that caught my attention that was published back in 1977. It was an American physiologist called Bill Hickson, and he did a study where they trained, I think it was 8 participants, as hard as they could for 10 weeks in their study. And the astonishing thing about this particular study was it encapsulated in their title, and they said they got linear increases in fitness across the training period. And what this line shows you here is the group of participants. It's how their fitness increased on average across the training study. So this line here shows you the 10 weeks of training. So this is week 1, week 2, week 3, and so forth. And then these are the average fitness scores for all of their participants grouped together. So they started off here down at around 3, or using these units over here, it's 3,000. And then they increased so that by the end of the study, on average, these participants had gone above 4 litres or 4,000 units. So that's an increase of 1,018. Now, what's extraordinary about that is they had about 8 people. They increased by about 1,018 units in 10 weeks. And then you look at this study, this massive study in America that was done, and here they've got maybe 1% of their whole study group have increased by that same amount. In this study, that's the average result. And they were headlining their study by saying, we get linear increases in fitness, which is what caught my attention when I was a student reading this paper for the first time. So what it tells or suggests to me is that what we're actually seeing is it really does depend upon what training you do too. This fact that these people can get all of their participants into that little group right on the end there suggests that they've done something fundamentally different in their study to what the standard physiological studies are done. This is a well-respected, highly regarded study with good scientists doing good science. There's nothing wrong with this at all, but they're getting nothing like the kind of improvement in fitness. And of course, most people are doing exercise because they want to increase their fitness. And here's something giving us a bit of a clue that, well, maybe there are some obvious things we're overlooking here. Now, I don't know what the answers are. As I said, I put these, I kind of throw out these little hooks for you to come back later on. But having read this study quite carefully on a number of occasions, a couple of things that were interesting to note on this. The first one was the scientists involved in the study were so curious about their results that after 10 weeks, they went to their participants and they said, we know you only signed up for 10 weeks, but would you mind carrying on so we can see whether we can keep this line going? And to a person, their participants said, no, your program is too tough. There's no way I'm continuing any further. And they actually wrote this into the paper. So although they got these fantastic improvements in fitness, it was so brutal a regime that their participants weren't prepared to continue any longer. It was well beyond what they'd signed up for. So that kind of maybe suggests one thing that's key to us. And then the other thing was that these people, when you look at how often they trained in the study, and compare it with all the other studies that I've mentioned previously, this was at the higher end. So they were doing 6 days a week, 2 sessions a day on occasions. It really was a punishing schedule. So there may be, again, some hints to look at there in terms of this question. So as I said, I'm interested in this area and I don't have all the answers, but there's very much something I'm focused upon in my own research. So as I kind of move to my final few slides, just to give you a kind of insight into where I'm headed, not the answers, but where I'm headed, I just thought we'd look at the kind of concepts of the question of how we might improve that training response and the sorts of things we might look at. Just before I do that, any questions on the previous slide? I realise I've skimmed over a lot already. Michael, I'm kind of doing your job for you, aren't I? Because we're going to do Q&A. Okay, fine.
I'm happy.
Yes.
I just wondered if the data that you're looking at is male or female, and if you have looked at both, especially around the age.
Yes, it's a really, really good question and a really important question as well. And I suspect part of your motivation for asking is you may be aware that there's a huge gender bias in the recruitment of participants. And so in terms of what I'm presenting here, the heritage study, which is the big genetic study, has a reasonable gender mix. The previous one that I'm looking at was mostly males, as far as I can tell. It's an older study, so it wasn't even reported so much there. From working with elite athletes, you would say that you would expect women to respond just as well to men through training, but that the ceiling will be a little bit lower. And typically, I mean, I kind of go on a rule of thumb of around 8 to 10% difference in performance. So where you see a male performance, a record performance, for example, where there's a difference of more than 8 to 10%, that suggests at some point you're going to see some kind of balancing out. Either the women are going to jump up because they've been underperforming, or you've had an exceptional woman that's set that record, and it will, you know.
And would you expect women to reach their peak at the same age?
So the analysis that we did on the cycling was the men's European peloton. So we haven't done a similar exercise for women. So it would be very interesting to do the same thing. The difficulty there is one of the ways we were able to do that analysis is because we could get so much data. For women's racing, because the participation numbers are smaller, it's going to take us longer to gather enough information to get a really clear picture emerging in the same way. So it's not a reason for not doing it at all. It's still an important issue and an interesting one too. But that's why we didn't try it in the first instance. It was quite a painful process. We had to hand clean a lot of that data. That's why I say it's, you know, I like to say yes, James and I did it together, but actually he led in doing a lot of the hard work on that. And actually one of our colleagues, Christina Dietz, did a lot of the computing side of it too. So one of the really interesting things, and this is perhaps where I can bring it back to home a little bit closer, is to think about an individual training session itself, just one training session on its own. And so one of my colleagues who I referred to earlier, Sarah Coakley, as part of a study that she did, brought a group of participants into the lab and asked them to ride, all of them to ride at the same intensity. So we measured their maximum and then we said, right, now what we're going to do is ask you to ride at 70% of your maximum. For as long as you possibly can. Now, the reason that's important is because typically that's the way we suggest people standardize their training. So if you've got a group of different athletes who have been coached by an individual, the coach may well set training intensities based on percentages of someone's maximum. So in the same way as we're looking at here is 70%, the coach may well suggest training intensities based around percentages of maximum. They may use different units, so they might use power output, they might use heart rate, they might use lactate or whatever it is, but essentially they're working from percentages of maximum. So it's kind of a similar scenario to what we see here. Now, the key thing here is, though, we should then look at how long these people can go for. So what we've done is say, at the same percentage of your maximum, each of you go for as long as you possibly can. And what you can see here is these are the different participants here. So this is participant number 1, and that's how long he goes for, nearly 50 minutes. Participant number 15, because we've ranked them on how long they went for, manages around about 10 minutes. Now, this is supposed to be the same intensity. So we would expect, normally, that they should all fall in pretty much a straight line somewhere in the middle. But in actual fact, I think what you'll agree is what we see is a huge diversity in people's responses to what's supposed to be the same exercise intensity. So in other words, what it's telling us is that when you specify somebody's training and you give everybody what you think is the same session, a fixed percentage of your maximum, they actually find it very different in terms of the challenge that's presented. Some people will find it really tough, like number 15 here. Other people will find it really quite straightforward and they can keep going for an awfully long period of time, like this person here. And although we did this study fairly recently, it's not a new finding, if you like. There's a classic study actually done on well-trained endurance cyclists from back in the 80s that has shown exactly this same pattern emerging and tried to explain the underpinning physiology as to why that should happen. But this has potentially quite profound implications then for our training, because if this is your standard training session that your coach has set, and he's got two different athletes, and one is athlete 15 and one is athlete number 1, that training session is going to feel very, very different to them. And that might explain some of the difference in responses that we've seen from those previous studies. They're all specifying their training as percentages of maximum. But actually, one person is finding it so easy that they could have done 50 minutes, but they weren't given the chance. Another one is going, I'm struggling to finish this session at all because this is really, really tough. You had a question?
I was just saying, is that related to what your maximum power is?
Yes.
Somebody like Marcel Kittel could produce like great 1,500 watts or something.
Yeah.
Be able to keep up 70% of that for anywhere near 50 minutes.
No, that's right. When we tend to standardize these maximums based around laboratory test protocols. And what we often ask the people to do is to ride or run increasingly fast until they hit a peak. But the test typically takes around about 10 minutes to complete. So someone like Marcel Kittel, although he would have an incredibly powerful sprint, because it's a 10-minute test, he's not able to use very much of that sprint at the end. He's kind of running out of gas rather than being able to use that sprint to keep him going for a long period of time. If we were to say just do a 6-second sprint, then you would see that peak power coming in a different way and a completely different distribution on this. But it would probably be equally biased, but in a completely different way. The point here really is that the way that we specify training at the moment doesn't really seem to work. And actually all those training studies are showing we're getting these very divergent results. But part of it is probably because of the way that we're actually setting out the training programs in the first instance. So we're kind of learning the obvious lesson that we need to tailor sessions to the individual. We can't make generic prescriptions. But we're quite some way from actually nailing what that answer is. And you look like you're about to ask me a question related to that.
To what extent can you separate out physiological and psychological? If you ask someone to go for a long time,
Yes.
some people just crack mentally.
Yes. So one of the slides that I wanted to put into this, but I was trying to keep to 30 minutes, honest, was a recent study that a colleague of mine has done, Professor Sam Makora at the University of Kent, where he's compared the mental fatigue that occurs during exercise. What he's done is kind of use a reverse model where he's given people a mentally challenging task. And so one of the things that you were sadly spared tonight was I was going to give you a mentally challenging task. So I could put up on the screen, if you like, a series of colours. And then ask you to put your hand up when a certain sequence appeared. So you would have to kind of concentrate on each colour being flashed up and then go, what was the sequence that Louis said he wanted to see? Was it red, green, yellow, and then I put my hand up, or, and then I'd go red, green, and then another green. So, oh no, I don't put my hand up. And then I'd say, you do that for a period of time, and they'd say, okay, how do you now feel having had to kind of concentrate on that for just a couple of minutes? How would you feel if I asked you to do that for an hour or more? And the answer is that what you can show is that that cognitive load becomes significantly fatiguing over a period of time. Now, the fascinating thing that Sam Makora then showed was that if you ask people then to exercise after they've done that kind of task, their exercise is compromised. So perhaps not entirely surprisingly, what happens is people perceive that training session to be tougher than normal, and they fatigue much earlier. Now, their muscles haven't changed at all. All they've done is use their brain, but the cost of working hard mentally has increased their perception of effort and means that they fatigue much earlier. This most recent study, what he did was he compared a group of elite cyclists with a group of recreational cyclists, and he showed that the elite cyclists were more resistant to fatigue. So given that cognitive challenge beforehand, they then went out and produced exactly the same performance as before. Whereas a recreational cyclist said, no, I'm really tired now, I can't repeat the same thing. So the mental side of these things is also very important, and it can have quite a profound effect. And there's a suggestion that actually, under these circumstances, what happens in physical training is that part of it is we're building a mental resistance to fatigue too. So it's important that we don't ignore the mental component of that. And actually Sam's done a little bit of work where he's superimposed mental training on top of physical training and suggests that people get more benefit from doing that than just doing the physical training alone. So there's all sorts of things going on in this, which is why the whole training conundrum is not simple to unpick. Sorry, that's a very long answer to your question, but I hope it's kind of given. Did I hit the bit that you were really interested in? Okay.
Is what you're saying elite cyclists are smarter than everybody else?
Well, interestingly, the actual cognitive test he gave them, they did perform better in.
Well, there we are.
But I'm not sure that means elite cyclists are smarter. I think they just, it might be context specific. But it's a nice thought, Michael. I'm sure it's one you'd appreciate.
Yes, yes.
At the back.
I think it's the same question, but when is the endpoint exhaustion to perceived effort and for the physiological response for this particular study?
So what is it, did you say?
What is the endpoint?
The endpoint. So what notionally what we do is we ask people to give us a rating. There are two different scales, but for simplicity we'll say it's 0 to 10. And when you get to 10, that's the maximum effort that you can sustain. Yeah, absolutely.
More interesting to do with lack of threshold or some physiological measure. I think that would be interesting to see.
To get people to exercise at percentages of their lactate threshold. Yes, yes. Yeah, no, you're absolutely right. It's probably getting a little bit technical for some people in terms of that. But actually, I have one of my colleagues here in the audience, Kieran, is looking at something quite similar to that for his research. Looking at different ways of trying to structure training sessions to see whether we can find a way that individualizes them, but in a way that we can still generalize across lots of people. So, for example, measuring people's lactate threshold and then setting exercise intensities off that would be an interesting way of doing it. Yes.
And I knew that actually my numbers were like way higher.
Yes. And you're right. So the classic study I referred to earlier was done by Ed Coyle in 1988. And what he did was he measured people's lactate threshold as well as their maximum. And he found those people that went longer had higher lactate thresholds. So there's a suggestion, there are some hints as to the sorts of things that are important. But at the moment, it still doesn't tell us what the optimal training effect is. It just helps us explain why a specified training session might be highly variable for different people. So as I try and draw to a conclusion, one of the things that struck me is that it kind of comes back to a point I made early on. We're now getting an awful lot of data and information on athletes. And athletes are routinely collecting this data themselves. And it struck me that actually if we could mine this data, the training data, in a sort of similar way to the way we've looked at the performance data at the start, perhaps we could understand something more about training and what comprises successful training. So one of the studies that I did recently was to get a group of 14 runners, and they recorded all of their training for a year with GPS devices. So every single running session they did was recorded on a GPS device. And now, of course, we can do exactly the same thing with cyclists too, and not only the GPS, but we can measure their power output, their heart rate, their speed, and so on. So all of a sudden, we're looking at large bodies of data which describe the training that someone's been done. And then the possibility might then become apparent that we can mine that data set to find out which bits of that training were more effective than others. So completely reversing the model where we're setting the training and then seeing the effect. Here, we're just measuring the training and then determining the effect based on whatever happens in those particular athletes. And I kind of put this slide up to show you, this would be an example of one runner, and each of these kind of squiggly lines that you can't really see properly is one training session. And so for 1 year, this is what one runner's training looks like. So that's an awful lot of data. And then if we do it for lots of athletes too, then we're looking at a situation that looks like that slide multiplied by several. And if we're then starting to try and analyze all of that data, then perhaps we can start to find a way in which we can pick out which aspects of training are more successful than others in a way that we can then generalize and help guide athletes with. And so one other point here as well is that if you were a coach working with athletes, there's no way that you'd be able to keep track of all this data, make sense of it and interpret it, incorporate that back into the way that you guide an athlete's training. But by analyzing that data on a computer, of course, then it may well be possible. So one of the things that I did recently was working with Yanis Kosmidis, who's a statistician at UCL, just a few streets away over here. And we took all of that data and tried to find a way in which we could simplify it, because you can imagine looking at all the data on that previous slide there, that's pretty tricky. But how can we simplify it in a way that we could then start to do the number crunching and the stats on it? And this is an example now of actually one athlete's training divided into different quarters for the year. So we were able to look at the change in performance for the first quarter of the year, the second quarter of the year, the third quarter of the year, and the fourth quarter of the year. But these blue lines here represent give you two representations of all of the training for that quarter. So these lines here, or those lines there, they're two versions of the same thing, describe all of the training that athlete did in that period of time. And what we then said was, well, which bits of this training, what speeds contributed to the change in performance we saw here, what speeds contributed to the change in performance we saw here, what training contributed to the change in performance here, and so on through that. And to my surprise, we were able to actually pick out in a group of runners significant speeds that dictated or related to the changes in performance. In other words, there were certain speeds we could say for that group of runners, the amount of time they spent training at that speed related to their change in performance. So it's the first, if you like, hint of what may become possible, where in the future, our training devices gather data on us, but they don't just sit there passively recording. Actually, what they'll do is, after the first ride or run, they will gather that data and then they'll be analysed, and then the device will switch its function and actually start prescribing instead. So it will say, speed up, slow down, go faster, change your route, whatever it is, because it's actually tailoring or optimising your training to maximise your own performance based on your own data, as opposed to necessarily being set by a coach. Now, that doesn't mean to say we won't need coaches, because it will be far more complicated than any computer algorithm can do, but at least it may help us to get a little bit more information out of the data that we have here. And then one a little extra bit that I couldn't resist putting in here as well is it might be an interesting tool also to help us detect cheating cyclists too. Because if we get to know what we would expect to be a normal response from ideal training, then we could spot somebody potentially who is in some way defrauding that system by manipulating some aspect of their performance, for example, taking drugs. So they may then start to stand out as an unusual response from all of their data. And when you're dealing with that large amount of data, it may be very difficult to manipulate that to hide what you're doing. So if you are taking drugs and you're responding unusually, which is the whole point, you're trying to accelerate your responses, then that would be an awful lot of data to try and manipulate to hide that fact. So one of the things that we've also done is talk to the Cycling Anti-Doping Foundation, part of the UCI, about the possibility of using these methods or developing these methods in that way. So my very last couple of slides now, I thought I'd just show you the evolution of an actual elite rider. This is based on someone who, like Michael, has now moved into the media. So but the benefit of this was at the time we gathered this data, there was no real longitudinal observations on elite riders. So what we have here is the laboratory tests for this rider from 1991, when I first started working at him, with him, right the way through to 2008, the Beijing Olympics, and a little bit beyond, which was when he then retired shortly after that. And he doesn't mind me saying who it is. It's Rob Hales, who you may hear joining the commentary teams on various occasions. So what I've done really is said that his first performance in the lab, we'll call it 100%, that was his maximum. And then we're looking at how his performance has evolved over time. Now, those of you that are vaguely familiar with Rob will know, and Michael can probably give us rhyme or verse on his Palmares, but he's a multiple Olympic medalist. He actually won the British Road Race Championship one year. So he's a hugely successful rider, albeit largely on the track. What we're seeing here is his development over a period of 17 years. His first test being, as I said, 91 up to about 2008, 2009. And if we just pick out his first performance and then his highest performance in the lab, what we can see is that over a period of around 17 years, he's achieved a 17% improvement in performance over that period of time. So this is the kind of data that we're only just starting to get our hands on now, for the obvious reason that it takes around about 17 years to track an elite rider over the evolution of their career. And so whilst we're now able to monitor riders quite routinely, for example at British Cycling, that kind of pattern of scientific quantification has only happened in the last few years. So we'll understand this process much better in a few more years' time. But this kind of data is still fairly unique in terms of looking at the evolution of riders over that longer period of time, which is why I wanted to share it with you. And obviously to finish off in that context of saying that's how much an elite performance is ahead of the normal person, this is the kind of improvements we can expect. And presumably this is somebody who's got his training right over those 17 years to be as successful as he has. But he's achieved largely a 17% improvement over that time as a consequence. And then my final thought is that once you've got all of those things right, I couldn't resist a couple of pictures that I found of Rob. The first one indicating that he doesn't always necessarily make the right choice when it comes to bikes. So this is Rob here on his chopper. And so clearly getting the right equipment and refining your cycling position is an important part of the performance as well, as we saw in the hour record. And then the final thing is, of course, you've got to learn how to ride it too. And Rob famously managed to fall off in the Olympic final in the Madison when he was riding with Mark Cavendish, I think, when they did actually manage to, he got back up and they managed to get the bronze medal. But I thought that would be an appropriate point to finish. And thank you very much for your attention.
Thank you, Louis. Absolutely fascinating. We've got a little bit of time for a few questions. Shall we sit down? Does that work?
I'm happy to. Yeah.
Oh, we shall sit down then. I've got a couple of questions, but why don't we? Is there any questions from the floor, kind of that follow straight on? Because yes.
Basically, going back to the very beginning of your talk, where you had your wattage data for the hour record, and you were also talking about modelling in terms of computer modelling. Have you ever tried to model things like Eddie Merckx's hour record, or going further back like Anquetil, or to see if you can work out what you think their wattage would be and how it compares to now?
I personally haven't done that, but because of the way that the UCI changed the rules after the hour record of Boardman's there was some attempts, because essentially what they tried to do was to force people to ride in a Merckx-style equipment, including even the hairnet and things. For a few years. So there was a bit of work that was done, particularly by the professional teams supporting riders that were thinking about going for the hour record and showing the added cost of that. But I haven't gone back and done that myself to, if you like, extend the power up figures back in performance terms. He did. I think it was in 2000, just before he retired. He popped up and this is probably an area that Michael would be able to comment on in more detail than I.
Yeah, but he went back to doing the Merckx position setup in 2000, and I think the reckoning was that record was about 420 watts when he went back to attack the Merckx record, and he just broke Merckx's record off that by 10 meters, I think. So that's kind of fits in with the model. Can I ask? I am going to ask a question. I am going to ask, given you talked a lot about training and how you model training and how you work for. Now, I interviewed Dr. Alan Williams from Manchester Metropolitan University a couple of years ago, who has done a lot of work in genetics. And I asked him the question everybody wants to know the answer to. I said, how much of it is genetics? How much of it is hard work? And he said, well, actually, it's almost exactly, he thought, 50-50. He said, that's not a number he pulled out of the air. He did the work. He did the maths. He said it was 50-50. If you improve training, does that change that balance? If training gets better, does it make it easier for someone with perhaps not exactly the right genetics to make it as an elite cyclist?
So which bit of that, because there were multiple steps in the question. What's the bit that
you're
you
a clever
want
chap.
to
No, the question is, if training gets better, does that make it easier, not easy, but easier for someone who might not have the perfect genetics to make it to the top of elite cycling?
I think if I were to give you a really short, concise answer, it would be no.
Right. Can I ask a really short, concise question?
Well,
just why?
Do you want me to qualify that?
Yes.
Which is that my suspicion is that we will find that there are some individuals that are super talented. And actually, I was struck by reading your own book
and
the description of your early experiences of cycling. and how fast you cycled at a very early stage in your cycling career. Feeling quite jealous and envious of the fact that you could get on a bike and go like a rocket when I'd spent 10 years struggling to perform at about 80% of the performance that you were able to achieve very early on.
If it's any comfort, I never really got any better. I started fairly good and I stayed fairly good.
But I think what we're looking for is that we recognise from that spread of those top 10 placings that actually there's a few riders, even in the pro peloton, that get a top 10 placing regularly or more than once. And they really are the creme de la creme of an already elite group. And I think that those people were probably born head and shoulders above everybody else. And then with the hard work, were able to get that extra little bit that then pushes them beyond their peers. So the optimal training moves those people, continues to hold them further ahead. So I think for us mere mortals, we can't necessarily expect to achieve elite status. But I do think that with optimal training, what we can do is surprise ourselves with what we can achieve. I've several times been working with riders who've been told by their coaches that rider has achieved his or her maximum potential. And I always think that's a very dangerous statement to make. And at least on 3 occasions that I can think of in my own career as a scientist working with cyclists, I've seen cyclists go on to surpass that performance that they've been told was their very best performance. And not just through technological innovation, so not just because they're riding a faster bike or a more aerodynamic position, but they've improved their training and their fitness too. So I'm always very wary of any attempt to set what the limits are. I prefer to kind of live in this world of opportunity and possibilities, set the context and try and allow people to achieve the very best they can. And looking at ways of modifying training, I think is one of those. And then just one further observation, very, very long-winded answer to this. But
it's a long question, as you pointed out.
One of the things that I'm struck by, and this is also a very personal reflection too, is that many people are very reluctant to experiment with their training and try very radically different methods or strategies and that kind of thing. And I think that will constrain us too, because what we'll find is that different people will probably need very different types of training session to move forward. And if you don't experiment with different types of training and try things out, different balances, mixes, length of time, interval sessions and that sort of thing, you probably run the risk of not finding those sessions that will really enable you to achieve your full potential. So I think some of this is also those riders that follow the tradition, for example, will be the ones that perhaps don't get the chance to achieve their full potential unless they happen to be the ones that the traditional approach works for. There may be other people out there that would benefit much more from a completely different approach, and trying to find out what that is and how we get a handle on it is a real challenge.
Can I ask a topical follow-up question? Which I was going to throw it open to the floor, but I want to know the answer to this. Which is, if you look at Team GB at the minute in Rio, being very successful and having their performances questioned by several other teams, and one of the answers that they have given is, well, we just focus on the Olympics once every 4 years, that's what we're about. I know some of the coaches and the staff at Team GB who talk about the fact that they train for a 4-year cycle. Mm-hmm. Is this one way does this work, do you think, as a means of optimizing performance? Instead of most athletes train on an annual basis, they start early in the year, they train to the Tour de France, they train to the World Championships, they take a break, and they repeat the cycle every year.
Yes.
Is it better, can you get better performance, do you think, by training on a longer cycle, so that you maybe spend a year doing endurance work, and then a year doing gym work, and then a year, or something like that?
I suppose the short answer is I don't know, but there's some interesting observations that I would make. Some of you may well have heard of Steve Peters, the psychologist that worked with British Cycling, Liverpool Football Club, and was it England
Ronnie O'Sullivan?
Ronnie O'Sullivan,
the English rugby team.
And I remember one day at a team meeting when I was working at British Cycling, him trying to offer the helpful perspective that cyclists generally are committed to working as hard as they possibly can at any given moment. So in other words, he was kind of suggesting that it might be a 4-year cycle, but actually at any moment they're giving their best. It was a very well-intentioned comment, and I completely agreed with the sentiment he was expressing. But the scientist in me also can't help but kind of challenge these kind of ideas. So I was sort of flipping this one around in my head, and actually I thought, I'm not sure that's true. I think actually there are times when we will go the extra mile and find extra resources and put the extra effort in. An Olympic year being a very obvious example of when that might happen. And so I think actually by working in a 4-year cycle, it's quite possible that you construct your training in a way that you don't end up scraping out all of your resources every single year, but actually leave yourself a little bit of breathing room so that you can push even harder for those very special events. So there's an element with which I think that might be an important factor.
But it's more complicated than
it's
just
much
purely
more,
physiological.
It's much more complicated than that.
Okay.
And the kind of one of the things I'd remind you out from the talk today was that study I showed you where they got this tremendous increase in performance with the eight participants, where they improved by the same amount as only 1% of the bigger study. Those people said they wouldn't carry on. Now, I'm sure they were quite happy to get fitter if it was just a question of doing training. They were saying this is such a tough regime, we don't want to sustain the work that's required to move to the next level. And as you get into elite performance, well, Michael, you're probably better positioned than anyone here to talk about kind of how much you have to sacrifice everything else in your life to squeeze out that extra little bit of a percentage. But Rob Hale's profile of 17 years and 17%, telling you you're looking for 1% each year. Again, I think it's hard to imagine exactly the kind of effort and focus and commitment that comes from this. But that's why I think working in bigger cycles might well be helpful.
Questions from the floor? I think we've probably got time. If Louis can keep it short, which the evidence so far suggests that might not happen, but we've probably got time for another couple of questions if Louis can keep it concise. We've got Sir here.
Yeah, hello there. I really enjoyed the presentation.
Thank you.
I'm now reflecting on the paucity of science at the fraction. So
good.
We've looked at 2 studies that talk to us about training response, but in fairness, probably raised more questions than they gave answers. They're 30 or 40 years old.
Yes.
I just wondered why there's not some more recent science studies done.
Okay. I'll try and keep this concise as Michael has asked me. So 2 things. One is I've kind of I've taken a particular perspective in order to showcase my point. So there are a lot more studies available, but they say the same things, and they're guilty of the same kinds of issues that I've raised here. So it's not that there aren't more studies, more contemporary studies, but they're done in the same vein and they suffer the same limitations. So there isn't anyone that's addressed the kind of issues that I pulled out yet. So I think that's kind of perhaps that's the quick answer to your thing. Yeah.
And one last question. Do we have a last question? Ooh, no. Sir, yes.
You're talking about innovative training strategies.
Yes.
It's been very trendy in the last few years to stop doing all this with long endurance training. There's a few short bursts, and there you get that.
Absolutely.
So how happy are you with that?
I think if you're time limited, it's an excellent strategy. I think if you're seeking elite performance, then you probably need to mix your training up a lot more than is implied by just going out and doing high intensity work. So if you talk to elite coaches and athletes, they haven't missed that trick. They know the importance of high intensity training, and they do include it in their work. But it's carefully measured and timed, and so I think that I say if you're time poor and you're looking for effective sessions, then the message is a very helpful one. But for elite performances, it's more complicated than that.
I think at 7:20, I think we get chucked out at 7:30, so I think we probably ought to wind that up at this point. I'd like to say thank you very, very much to Professor Louis Passfield for his presentation.
And I'd like to thank you too. It's great to be able to sort of speak and pause and have people ask questions along the way. So you've been a real pleasure to work with today as well.
But thank you very, very much, Louis. I think we've all enjoyed it very much indeed.
Thank you.